welcome to our third lecture. Well, second, if unless you count the one that we did last year. But today we're going to be doing math and music, and our presenter for today, after a lot of switching, is Roy, who is also the director of the Princeton side of this program. I don't have very much to say. So, without further ado, Roy.
So, first of all, I have to apologize. I think beforehand you guys were told that today's lecture would be on induction, and the speaker had something come up today, and so he was unable to come. And so I decided to throw something together with math and music, and I think that music is especially like one big application of mathematics that we can see in the real world and interact with. So I want to start today's lecture off with a, I guess, sort of physics/biology lesson. How many of you guys play instruments? Oh, okay. So almost everyone here. Do you guys know what sound is? How do we perceive, when we play a note on like a piano or violin, how do we hear and like process that noise into a sound? Yeah.
Pressing the note or not in the mouth.
Right, so if you press a note, what happens? How do we hear that? And like when I talk, how do you hear sort of this noise that I'm making? Yeah.
Sound travels through waves, so when it goes into your eardrums, like your ear perceives different vibrations.
Yeah, exactly. Exactly. So sound is, I guess, propagated through waves, and we have an air pressure around us. And sound is pretty much a contraction or expansion of the air pressure around us. And this air pressure, when it gets into our ears perceive this pressure differential as a noise. And so when I'm talking, for instance, my voice box or larynx is constantly, the muscles in my voice box are constantly expanding and contracting and making a change in air pressure, which you guys then perceive as words that I'm saying. And so let's look at a particular piece of audio and see what exactly this pressure differential is like.
I find your lack of faith disturbing.
Can you guys all hear that? Okay, let me try. Raise the volume.
I find your lack of faith disturbing.
You guys all hear that? Just by random chance. Do you guys know what that's from? Yeah.
Star Wars.
Yeah, exactly. And so, so it is Star Wars. And if we were to plot this data, we'd get something like this. So, does someone, or can anyone give me like some observations they see about this particular graph, which is the sound that you just heard? Let me just expand. Just any observations at all about this graph? Yeah.
It looks like a weird shape.
Okay, so how is it weird?
I don't really.
So why did you say that it's a weird shape? Just anything that makes it out of the ordinary.
Because in some places it's because in some of the it's like there's like more of
Yeah, exactly. So if we see peaks here and like peaks there and there, and it's not a uniform, I guess, peak all around. Any other observations? Yeah.
it's not symmetrical up and down.
Yeah, that's true. So we see here like these peaks are different, and so it's not exactly symmetrical. Anyone else? Make any observations at all?
Can you play the audio again?
Yeah, sure.
find your lack of faith disturbing.
So what do you guys think these peaks are? Yeah.
Maybe words.
Words. Yeah, exactly. And so yeah, and sound. And what this I guess if you think that these peaks are words, which they are, what would be a guess for the y-axis of this graph? Yeah.
Time.
So time is actually the x-axis.
Yeah, time. I got confused. Then the x-axis is.
Or the so this is the y-axis.
Yeah, the y-axis is the amount of words.
Yeah, exactly.
Or something.
Yeah, so the y-axis is going to be the amplitude of your sound waves, and we perceive amplitude of sound waves as the volume of the sound. And so at these peaks, we hear louder noises because that's when the words are being spoken. And for instance, at the very end, we see nothing because there's no noise there. And if we were to expand on just part of this graph, this is a close-up of the segment 2000 to 3000. So I'm just blowing up this tiny segment, and we get this type of graph. Scroll down. So can anyone make any observation about the graph now that it's expanded? Yes.
I think when it is above the y-axis, it means there is a higher pressure and something about that.
Yeah, exactly. So when I was saying before, this y-axis is the amplitude of the sound waves. But as I mentioned at the very beginning, sound is it travels through sound waves and the contraction and expansion of the air pressure around us. And so what this y-axis is actually is the difference between the sound or in the air pressure relative to some, I guess this is the average air pressure around us. And so at points above, we have a, I guess, higher pressure, and then at points below, we have lower pressure. Does anyone else want to give me an observation about the shape of this graph? Someone who hasn't talked. Yeah.
When it's closer to the end, it goes higher up and down, which means that there's like more of a change in the
Amplitude?
Yeah.
Yeah, exactly. Do you know what the word is for exactly how fast it goes up and down? Yeah.
frequency.
Yeah, exactly. So frequency is measured per second, and it measures pretty much how quickly it travels up and down per second. And so right here we see that it's relatively low frequency compared to over there where there's especially a high number of frequency. And then I want you to just look at this oscillating sound. So, or this oscillating shape. Does anyone know, and this may be too advanced, but does anyone know what kind of shape this is? What kind of function?
A sine wave?
Yeah, exactly. So normally that's like 10th grade type stuff. I don't expect you guys to know. But this is a sinusoidal wave. And if I graph a sine wave like this, so this is a sine wave that I plotted, and then I will play this data. Okay. That should work. So I'm gonna play this sine wave as a noise. Does anyone have a guess what this sign or what noise we'll hear, what properties of this noise. Yeah.
It'll be like an even note,
An even note.
like
What-
meaning it won't change much.
So why do you say that, even though it goes up and down?
Because the distance between the peaks and valleys are the same, will appear to be the same. So it occurs at the same frequency, like meaning the changes.
Yeah, exactly. So it's the same frequency. And so you're touching on the point that what notes and pitches that we hear correspond to frequencies. And so if this has the same frequency all throughout, you're saying that we'll hear the same pitch and the same note throughout, right? And if we play this, oh, why is this not playing? I apologize. Your function. Should just be this. There we go. So yeah, we see that it is one note throughout. Just randomly, does anyone know what that note is? Oh, this is 400 hertz, by the way. I think it's A, I want to say, middle A.
440 is it.
Oh, 4/4. Okay, never mind. I lied. Okay, so we talked about how pitches that we hear correspond to frequency. And so if we wanted to take Darth Vader and make him speak in like a chipmunk voice, how could we make him do that? Yeah.
Essentially speed up increase the frequency.
Right, so we want to take a whatever he's speaking, this graph, and then increase the frequency of this graph. And so, I guess just like, sort of in your own words, how do we increase the frequency of a graph like this? Yeah,
You compress it.
what do you mean by compress?
So you take the whole graph and then you shorten it to a smaller amount of time.
Yeah, exactly. So we want to sort of like squeeze this graph together. And one way to do this is, I guess, I'll just play it first, to be honest. If we compress it to this, so I already pre-compressed it, or increased the frequency. And then, so the blue was the original Darth Vader, and then I cut it in half the time and sort of like pushed it in half the time. And the orange is the sort of like compressed one, as you can see here. And I'm going to play it right now. So what do you guys notice about that? Yeah.
We pretty much can't make anything out of it.
Right. So even though we increase the frequency so that he speaks at twice the frequency, what happened to the time of this, or the audio length of this file? Yeah.
It's much shorter time.
Yeah, exactly. So since we compress it, we use this audio file is in half the time, which means even though he'll speak higher, he'll speak twice as fast as well. And so actually this is a very hard problem in terms of how to increase the frequency of and make someone speak in a higher pitch while still maintaining their speaking volume or speaking length. And I guess there are many theories and algorithms to do so, but in general, it's a hard thing to do. Yes.
But like on YouTube, like you can like when you go to the settings, you can change the speed of the video and it still has the same sound.
Right. Yeah. So I think. So again, what they're trying to do is, so they try and compress it like this, and so this would be double the speed, but you want to make it at the same frequency, and so I think what they do is sort of cut out sort of like, if we look at a sine wave, they sort of, actually I don't know exactly what they do to make it longer, but I think they most likely, if we look at a sine wave and double it, so if we plot 2 times. So if we take this, so this is double the frequency, they probably somehow like make it half the frequency by interpolating. I'm not exactly sure. You should look. I can look it up afterwards, but I think that's what they do. All right, so let me first close this for now and start drawing. So I guess what we were doing is interpreting the sound waves as functions. So this time, and this is going to be our some function f of t. And then this is some sine wave for some pitch. So we said that by scrunching this sine wave together, we can increase the frequency and also increase the pitch. So does anyone know how to represent this as another function? So given that this is a function f of t, what would be the function that is sort of double the frequency? So what would this green function be in terms of f of t right here? Also, I'm sorry if I drew it poorly. Yeah.
F of 2t.
Yeah, exactly. So f of 2t is this graph. And if we wanted to sort of halve the time, or half the frequency, like this, I want to say. What is this function? If the green one doubles the frequency and is f of 2t, and the blue one halves the frequency, what would be the function?
F of a half t.
Yeah, exactly. So this would be f of t over 2, 1/2 t. And so if I write my function as f of t is a sine wave, so sine of let's say 400 t, then does anyone just want to guess what the frequency of this would be? Frequency of this function, sine function. There's really only one number. Yeah.
400 units.
Yeah, so it's 400, and the units for frequency is hertz.
Yep.
So it's 400 hertz. And now we can see why exactly f of 2t is double the frequency, right? Because if we plot f of 2t, this is sine of 400 times 2t, which is sine of 800t, which means that this is, what's the frequency of this? Yeah, 800 hertz. Right. So here we see 400, and if we do twice the time, we get 800, and if we do half the time, we'll get 200 hertz. Right. Let's see. All right, so viewing these as functions, we hear multiple sounds. There's never, so you hear me speaking, you hear the hum of the projector, you maybe hear some of your classmates talking. And so suppose that f of t is the sort of sound wave corresponding to my voice. And then g of t is the sound wave corresponding to, let's say, this projector. What do you think, just like as a guess, would be the sort of sound wave that your ears hear? So the combination of my voice and the projector. In terms of F and G. Yeah.
GT?
What do you mean by FGT? So this is a, yeah, so can you expand on that? Do you want to, when you say FGT, do you mean multiplying the two? Like adding? Yeah, exactly. So the sound wave that I hear is, or that your ears hear, is F, is a new function called, which is the sum of the previous two. So F of t plus G of t. And we will be able to see that. So, so we have Darth Vader speaking, which is audio, and then I imported a cattle noise like this. And if we were to plot, or if we were to play both of them, which is, so audio is Darth Vader plus the sound wave, which is this cattle that I just played, and play the two.
I find your lack of faith disturbing.
So right, we hear both of them overlaid at once. All right, and so let's say hypothetically I'm a recording artist and I'm playing a guitar. And while I'm recording my guitar playing, some person comes in and then just like starts shouting in the middle. So representing that. So if I have F of t, which is like guitar, and then G of t, which is this interruption, then when I'm recording, I have the recording gets them combined, which is combined is equal to F of t plus G of t. Suppose that I have the audio file corresponding to this combined, so both the guitar and this person shouting. But suppose I also have G of t, which is an interruption. How could I get just the guitar playing again if I want to get rid of the guy speaking? If I have F plus G and I have G. Yeah.
Subtract G of t from both sides. So you'd have F of t. Then when you subtract G of t from the combined, then you get F of t.
Yeah, exactly. So if I do combined minus G of t, I get just F of t back, which is what I want. And if we were to try this out, so I'm going to call this combined. And then, so combined is just,
I find your lack of faith disturbing.
and if I were to just do combined minus this kettle noise, then I just get,
I find your lack of faith disturbing.
so I completely get rid of that external kettle sound. So I guess when we think about math, we always want to think about how can it be applied in the real world. And what do you think is an application of this noise cancellation? Yeah.
Filmmaking?
Yeah, so filmmakers use this. But how about something in like that you would use on an everyday basis? Maybe when you're listening to music, if you have a special set of headphones, maybe? Yeah, exactly. So noise canceling headphones. So so how noise canceling headphones is you play it, you turn it on, and then it cancels out the noise that you hear from outside. How do you think it does this? Like from what we learned.
I know.
Okay, so someone else.
There's deconstructive interference, so the so basically the headphones play the opposite of what the interference is.
Yeah, exactly. So yeah, it's called deconstruct. What was it?
Deconstructive
Yeah.
interference.
Deconstructive interference, and these headphones have speakers on the outside, and they'll pick in the whatever you're hearing, and then play the exact opposite of that, so negative that, into your ears, and which will cancel out whatever you're hearing from the outside, and so you theoretically should hear nothing, hence noise canceling.
Except for your music.
Yeah, except for your music. Let's see. Yeah. What's up? Okay. Okay. And actually, so this is called deconstructive interference, and there's also something called constructive interference. And what do you think? If deconstructive is canceling out the noise, what do you think constructive interference is? Yeah.
Playing that exact noise so it makes it louder.
Yeah, exactly. And so, what I think this is used in theaters. Don't quote me on this, but I think what theaters do is they have the shape of the theater so that the noise from the orchestra will hit the back of the theater and then come back to you, and so you'll hear it from two sources: one from the orchestra itself and one from the wall behind you, and it'll be constructive interference, which means that you'll hear the waves will add and you'll hear a louder sound, pretty much. Okay, so this is all fine and dandy if we have sort of this opposite sound that we want to get rid of. But a lot of times, we don't have this opposite sound. For instance, if I'm just given a file of the combined Darth Vader and this audio, and this tea kettle. Let's see if I put it. Okay. Let me just plot it then. Let's see how to put it. This one.
So it means I copy paste.
Sorry. It's not a list of numbers. Okay, here we go. So this is a sound file of both Darth Vader speaking, which we heard before, and this kettle, which is shown here but also extends over there.
You just
can't really see it.
Yeah, exactly. You can't really see it. How would you guys suggest trying to get rid of this tea kettle sound? So if I only have this, how do I get the original sound again? Yes.
You take the other noise and then you get a function for it.
How exactly do I get a function for the other noise? I'm only given this now.
You zoom in.
What do you mean?
Like you look at it so it doesn't look like just a big shape.
Okay, so if I zoom in on sort of this part, how will I be able to separate the Darth Vader part and the tea kettle part?
No, I mean the tea kettle.
You mean this part?
Yes.
So, okay, so this is I can extract this, and this will be some sound. And then what do you want me to do with that?
You have to try to see what the sound will be if it's in the part where he's speaking.
So are you trying to say if we take this and then subtract sort of this part from that part?
Yeah.
I guess that sort of assumes that it's going to be, one, the sound is going to be the same throughout, and two, that we add it at the same sort of at the same phase, which means that it will be deconstructive interference as opposed to constructive interference. But that's a good idea. And I guess most ways are trying to find different ways of doing this. Does anyone have another idea of how we can try and get rid of this kind of sound? Yeah.
So first you get the part which is at the end,
Yeah. So this part.
and then you make the computer which is doing this. It would go online. It would look for databases, common noises. It would search for any sound with that part in it. Then it would take the full sound and use your other solution.
Yeah. Well, I guess that would probably work because I got these sound files
That's
online.
a lot of computer data, but I think it'll work.
Yeah, but let's say instead of having this kettle noise, someone is speaking over Darth Vader. So I'm recording a scene with Darth Vader, and then some cameraman is just like chatting in the background about what he's drinking today, like some coffee, let's say. And I don't think that's online. So what's another idea for how we can get rid of it?
We could go find the Darth Vader sound online.
Yeah, okay. I suppose we could just ask him to re-record it.
Yeah.
I think in general, this is like I guess in general, this is a fairly hard problem in order to separate these two sounds. Yeah.
Could you just actually? It's
Go ahead. What were you?
no, I mean I set whatever someone said.
Okay. Yeah, so in general, this is a fairly hard problem. And although we do know how to do this in a select, in very specialized cases, and that is through something called the Fourier transform. I'm assuming none of you guys have heard about that. It's probably good. Have you? Yes.
Wait, well then why can't we just like we split every time we split it into each frequency sound and its current amplitude, and then we play it again, and then we try to like hear the sound we're trying to subtract from it.
That's actually pretty good. That's the idea of Fourier transform, in that we take a sound and then we want to try and find the frequencies, and we want to deconstruct this sound into a sum of different sounds. So we take a given sound file and we deconstruct it into a sum of sine waves by identifying what the amplitude is at a particular frequency. Let's see, which one do I want? All right. So here I just have a normal digital wave, which is a very blocky, and what Fourier transforming allows us to do is transform this into a sum of different sine waves that we learned about. And so if I were to I guess let me first ask you. So given this wave, how would you deconstruct this into sine waves? So what would be like what would be like the major sine wave in this? Yeah.
A sine wave with an infinite frequency at the place where it's has an infinite, like it goes straight up and down.
Well, if it's infinite frequency, it'll be like, or close to infinite frequency, it'll be going up and down throughout the whole thing, right?
No, I mean like only for the part that's going straight up.
Well, what we want to do is, I guess what we want to do though is try and find this as a sum of sine waves that go over the entire interval. And so I guess I think a good approximation for a sine wave would be something that like starts off down here and then goes up here and then is like this, right? You guys admit this is a pretty good approximation.
Yes.
We have some areas down here and up here, but more or less this is what we want to do. And what Fourier transform does is it allows us to find this and then do and then find a sine wave which approximates the error and then approximates the error and continually does so. So I just want to ask, do you guys believe that we can represent this function as a sum of waves that look sine waves that look like this? You guys even believe this is possible? Yeah.
No, because it's just because there's a part and it's going straight up and down.
Okay. Yeah. So it seems pretty like unbelievable that we can actually do it. Here we go. Okay. Why is this not? Okay, I guess I just have to blow up this. Okay, so as I was saying before, let me just fix this. As I was saying before, this is like a pretty good approximation. So that's the first sine wave that we add. And if we add more, so then they're telling us to add this orange sine wave. And if we do it, we get something that looks like this. Right, so this is like a little bit closer to what we want. And just for reference, what we want is, I think, something like this. Something like this. Yeah. So now you see that we're sort of, before we were just underestimating everywhere. Yeah. So before we were sort of underestimating here, overestimating, and we have, yeah. And then if we add another sine wave, we get closer, and then closer, closer. Let's say 20 sine waves.
Scroll down.
I need to scroll down. Oh, nice.
Oh.
So as you can see, we still have this sort of sine oscillation that goes on top. But if you see here, right, what we saw as like a sort of perpendicular line is now getting closely and closer modeled as a sum of sine waves. So just erasing this part right now. Like that line looks pretty perpendicular right now, right? And so if we were to increase this more and more, let's say, so this is a sum of 50 sine waves. And these oscillations right here are going to probably be like small enough that we really don't hear the difference. And so we're able to represent what we originally wanted to represent, which is just a sort of block as a sum of, this is only 50 sine waves. And so this is the power of Fourier transformation. In terms of, we can get our original function from just recording only 50 of these sine waves and adding them all up again. Hmm?
Why is it called the 48 one?
Huh?
Why is it called the 48?
Oh, sorry. It's called Fourier transform. So that's F-O-U-R. And he was French, which is why it's like Fourier instead of like Fourier. It's Fourier. Yeah. You had a question?
So I see some errors on there.
Yeah, exactly. So this isn't exact, right? Because we still have some errors away from our original box, like these oscillations here, and then maybe like a larger oscillation there. But the idea behind this transform is that, or at least in terms of sound, is we can't really hear very, very minute differences, right? This is like a very, very small oscillation. And what did we learn about amplitude? So smaller amplitude means,
Quieter.
yeah, exactly, quieter sound. And so if we were to subtract our original function, which is this block, then we get this very, very small amplitude wave. And presumably we won't be able to hear what it is. And therefore, when we hear this, we will hear the same thing as if we were to play this block function. Scrolling out. Yeah. And so as you can see, as you go on and on, you get closer and closer to our block function. Yeah. So when we take a Fourier transform, actually I want to do this here. So let's try and see this in action. I'm going to be playing two sounds. One is a bass. And one is a violin. And this is both the sum of both of them. And so you can hear sort of like the bass at the lower end of the spectrum and then the violin at the higher end. If we take the Fourier transform, we get, so this is the Fourier transform of the violin. And so I told you before that the Fourier transform, what it tries to do is it tries and looks at each frequency or model a certain sound wave as a sum of sine waves, and it does this by looking at a particular frequency and then looking at what the amplitude of that frequency should be. And so on the x-axis here, this is no longer time, but now it's frequency. And this y-axis is amplitude of amplitude. So this is a violin, and can someone, I guess, make some observations about it? or like tell me what this graph is telling us. Yeah. Yeah.
Okay, what are the labels on the bottom?
Yeah. So this is
What's the amount of
frequency, which is measured in hertz.
What's the amount of those are the little logos in the bottom?
And this is 5,000 hertz, 10,000 hertz, 15,000 hertz. I guess this may be clear if I compare this to this. So this is the Fourier transform of the bass. This is the Fourier transform of the violin. Yeah.
It's basically a graph showing how loud the instrument was at a certain frequency.
Right. So what can we say about the differences between this graph, which is the violin, and this graph, which is the bass? Someone who hasn't spoken. There's something? So graph 1, bass. Graph 2, violin. Yeah.
The violin graph has significantly large values for larger frequencies than the bass.
Right. So if we look at this graph, we see high peaks at frequencies above, I don't know, let's say 2,000 hertz. And so pretty much all of the noise that the violin is making is noises at a fairly large frequency. And high frequency means high pitch, and that's why I guess violins are higher pitch than bass. But if we look at the bass Fourier transform, all of these are sort of below 2,000, right? All of these peaks, and there's nothing above.
Almost.
Yeah, pretty much almost nothing above this. And I guess this is telling us the bass, as the noise that a bass makes is at fairly low frequencies. And it's represented by the Fourier transform by saying that at these low frequencies, you have a sort of like a loud noise at these lower frequencies. And so if I have so I took a Fourier transform of the combined noise, right? Or I guess just as a guess or intuition, if I take the Fourier transform of the sum of two functions, what do you think the transform graph will look like? Someone else. Yeah.
Wider than any one of the functions.
Yes. Well,
Unless they're the same one. Then you can tell, because if they're the same one, then the amplitude's doubled.
yeah. So you're saying that if it's like the same amplitude or same frequency, then it'll add, right?
Yeah.
And hence double. And so that's pretty much is what's happening in that when you take the Fourier transform of a sum of two functions, you just get the sum of the two Fourier transforms. And we see that by, so this is a Fourier transform of both the bass and the violin. And this is of the bass only, violin only. And if we add the two, we just get this function. Yeah, bass is pretty loud. So now, knowing that the bass is going to be at predominantly low frequencies and the violin at predominantly higher frequencies, given this Fourier transform, how do you suggest that we separate the bass and the violin out?
it along a frequency line and then wire.
Hmm?
By splitting it along a frequency line, like one side is like mostly bass and the other side is mostly by
Yeah, exactly. So as I mentioned, so I said around like 2000-ish, like this line-ish, is where the violin cuts off and where the bass starts. So we think that the bass is contributing this part to the Fourier transform, and we think the violin is contributing this to the Fourier transform. And so the idea is that if we were to just take this part and then invert it back and sum the sine waves up together, we should get just the bass, right? And if we take this and then sum the sine waves up from this, we should get just the violin. Does that make sense to you guys? Let's see what happens if we actually do that. I use 2150.